In this video, we're going to talk about what semiconductors are and how we can use different types of semiconductors to make a device called a diode. We begin a discussion with what the atom looks like. We will use as basis our knowledge of basic chemistry using the electronic configuration. For the 1s2 configuration, we are looking at the first two energy levels or states which electrons can occupy. These are in the lowest orbital nearest to the nucleus. These are the two electrons with the lowest energy levels, but the highest energy required to remove from the atom since it is very close to the nucleus. For hydrogen, there's actually just one electron, but for helium there are two. The next state of energy which electrons can occupy with a slightly higher energy level is the 2s2 configuration. There are a maximum of 2 electrons in that energy level. Lithium's third electron will occupy one of these, while beryllium's 4 electrons will occupy the 1s2 and 2s2 states. Boron has 5 electrons. Its 4 electrons will occupy the 1s2 and 2s2 states, and the fifth one will occupy one of the 2p6 states. These states are also in the second energy level of the atom, since that energy level can allow a maximum of 8 electrons. We can continue with larger and larger atoms and fill in the available states one by one according to the nomenclature determined by the electronic configuration, as shown in the figure. However, the most interesting elements for us in this course are silicon and germanium. Silicon has 14 electrons, while germanium has 32 electrons. Silicon's 2 electrons will fill up the 1s2 states first, and then the 2s2 and 2p6 states, followed by the 3s2 and finally the 2 of the 3p6 states. Germanium's first 18 electrons will fill up the 1s2, 2s2, 2p6, and 3s2, and 3p6 states as well. The next higher states are actually the 4s2, followed by the 3d10 states. The next 12 electrons will occupy these states. The last 2 electrons will occupy the 2 states of the 4p6. Notice that for both silicon and germanium, the highest occupied energy levels are the 3rd and 4th energy levels respectively, both having 4 electrons with 4 unoccupied states. What are the implications of such electron arrangement? For these atoms, they have 4 energy states that are unoccupied. It will be easier for us to take a look at another way to represent silicon. We let the silicon atom be represented by the blue circle in the figure and 4 dots surrounding it. This type of representation in the chemistry is called the Lewis structure. This representation is convenient because we can show how the 4 extra electrons represented by the 4 dots are ready to bond with the other electrons. Thus, if you have silicon atoms arranged as shown in the figure, each of the electrons of each silicon atom is shared by the electrons in the other nearest silicon atoms, thus completing the 4 electrons required to complete the 2p6 states. All of these states that have been occupied by the electrons are called the valence electrons. The set of energies of these electrons is then called the valence energy band, or simply the valence band. The valence band represents the filled energy bands. The highest energy level in the valence band are the electrons. All of these filling of states and sharing of electrons are happening at room temperature, which means that there are no electrons with extra energy due to thermal energy. The energies that the electrons have in the discussion is purely due to the electrostatic interaction between them and the nucleus. This is an ideal picture of the atom. Quite ideal, in fact, since it ignores the interaction between electrons themselves. If extra energy is applied, however, the next energy level they are going to occupy are the lowest energy states of the conduction band. Thus, there is a certain amount of energy that the highest electrons in the valence band requires in order for it to jump to the lowest available energy state in the conduction band. This energy is called the band gap energy. Between the conduction band and the valence band, no electrons can ever be found. This is why it's called the band gap. The conduction energy band is a set of energy levels that are unfilled. Ideally, without electron-electron interaction, the filling up of electrons would just follow the electronic configuration as shown in the previous slides. If we add this interaction, then the conduction band is pulled slightly downward. This decreases the band gap and consequently the band gap energy. In some materials, the conduction band and the valence band overlap. These are metal materials. Electrons can easily transfer between the valence and conduction band without any extra energy needed. In materials such as silicon and germanium, there exists a small band gap energy between the valence and conduction bands. Such materials are called semiconductors. In other materials, this band gap becomes very large. Thus, electrons in the valence band requires a lot of energy in order to jump to the conduction band. Such materials are called insulators. The energy required by insulators cannot be acquired through thermal means and must be applied directly. A very high voltage would typically do the trick, but there will be no practical application for such materials other than act as an insulator. The table lists a few semiconducting and insulating materials. There is no straightforward delineation between band gap energies of semiconductors and insulators. The definition present here is very basic, and there's more to a semiconductor than just a low level of band gap energy. We are going to explore these properties of a semiconductor in the next few slides. For now, if you take a look at the table, you will notice that most materials with energy band gaps below 3 electron volts are semiconducting materials. Silicon and germanium are the only single-element semiconductors. They are called elemental semiconductors, along with tin, selenium, and tellurium. Tin, just like silicon and germanium, is a group 4 semiconductor, while selenium and tellurium are group 6 semiconductors. They only require 2 more electrons to complete the valence bands. These types of semiconductors are also called intrinsic semiconductors. There are also compound semiconductors, composed of 2 or more elements that are combined in specific proportions. These are obviously not naturally occurring semiconductors and are called extrinsic semiconductors. All other materials with band gap energies greater than 3 electron volts can be considered, but not strictly, insulators. This is the reason why diamond is not a semiconductor, even though it's also a group 4 element and requires 4 more electrons to complete its 2p6 states, just like in silicon and germanium. However, carbon has other properties that make it a great material. Why do we have other compound semiconductors? One specific property that makes compound semiconductors more attractive than elemental semiconductors is its band gap. Gallium arsenide has, for example, what is called a direct band gap. This means that electrons can easily jump from the valence band to the conduction band just by the addition of thermal energy. When the electron leaves, it leaves behind a vacancy state, which is called a hole. The hole is a type of quasi-particle. It also has a positive charge. It's not really a particle in the sense that an electron is considered to be. However, its behavior is like a particle, as we shall see later on. On the other hand, silicon has what is called an indirect band gap. In this case, additional energy coming from interatomic interaction, which we call as phonons, are required. You'll learn more about these things when you study solid-state physics. For now, I leave you with this idea that silicon is not at all the perfect semiconductor, but requires a little bit of tweaking in order to attain a desired electronic property. Here's how you tweak silicon in order to change the conductivity. If you replace a silicon atom with a group 5 atom, such as arsenic, phosphorus, or antimony, then 4 of the electrons will immediately form a covalent band with the 4 electrons of the surrounding nearest silicon atoms. There will be 1 extra electron. The energy of that electron is slightly higher than the valence band. If you put in a small amount of group 5 atoms and replace a few of the silicon atoms, you'll get a few extra electrons with that amount of energy. The energy is higher than the valence band but lower than the conduction band, and is much nearer to the conduction band. These energy states are represented by the dashed line in the upper figure. This highest energy state where electrons are found is called the Fermi level. In this case, when a group 5 atom substitutes a group 4 atom, these energy states are created, forming this new Fermi level. Only a small amount of thermal energy is required to bring these electrons from the Fermi level to the conduction band. When electric potential is applied, current is obtained through electrons that move around the silicon network of atoms, also called the lattice. This kind of semiconductor is called an N-type semiconductor. On the other hand, if silicon is replaced by a group 3 atom, such as boron, aluminum, gallium, and indium, only 3 of the 4 nearest surrounding silicon atom shares an electron with a group 3 atom. This kind of semiconductor is called a p-type semiconductor. In a p-type semiconductor, there is a vacancy present, which we now know we call a hole. A hole is the absence of an electron, thus its charge is positive. The energy of these holes is slightly larger than the valence band. Therefore, the new states created by the hole is the Fermi level and is represented by the dashed line near the valence band. Electric conduction occurs in a p-type semiconductor when an electron from another adjacent silicon occupies the hole. The electron that has now moved has left a positively charged hole. It will then be occupied by another electron from another adjacent atom, and it leaves behind another hole. Thus, it would actually seem that the hole is moving and behaving just like how electrons move around. We can take a look at this short video of how a hole moves around the lattice, just like an electron, and results to the electronic conduction that is observed in measurements. Pay close attention to how the positive charge moves around the lattice. When you put a p-type semiconductor with an n-type semiconductor together, the extra charges of the p-type semiconductor will be attracted to the extra electrons of the n-type semiconductor. They both diffuse within the material and gather at the red and blue regions. Since they physically combine, all holes gather in that small red area and all electrons gather in that small blue area. In order for them to combine, they have to overcome that small physical barrier, which would require some energy to do so. Thus, in equilibrium, there is a charge separation in that region. This is called the space charge region, or in some reference, the depletion region. The separation of charges creates an electric field pointing from the positive charge to the negative charge. Thus, these collection of charges form a built-in voltage or an electric potential barrier. In order for any charge to pass through, this electric potential barrier must be overcome, and energy is required to do that. This combination of a p-type and n-type semiconductor is called a p-n junction. If we draw an energy band diagram, this is how it can be represented. Before combining the two types, the p-type semiconductor is represented by a filled valence band with a small Fermi energy level just above the valence band, while the n-type semiconductor is represented by a filled valence band with a Fermi level just below the conduction band. Upon combination and before diffusion, you see the Fermi levels misaligned. The Fermi levels represent the highest energy level occupied by the charges of the atoms. Thus, these Fermi levels must align. You can therefore imagine that when the Fermi levels align, the p-type band moves up, while the n-type representation moves down. The final result is the figure to the right. Electrons are represented by the red circles, while holes are represented by the blue circles. For electrons in the n-type region to diffuse to the p-type region, it must overcome an amount of energy equal to the potential energy. In this figure, that energy is represented by Q phi sub I. For electrons in the p-type region to diffuse to the n-type region, it must overcome the same amount of energy. Where would these electrons and holes get this energy? In equilibrium, both electrons and holes are in the space charge region or depletion region. The corresponding energy band diagram is shown in the upper right figure. This time, the potential barrier is represented by EVD. If an external potential is applied across the p-n junction with the positive terminal on the p-type and the negative terminal on the n-type, then this configuration is called the forward bias. The positive terminal repels the holes in the p-type and attracts the electrons on the n-type. This decreases the width of the depletion region and subsequently allows for diffusion across the junction. In terms of the energy band diagram, this is represented by a decrease in the potential EVD by the applied potential EV. The applied potential raises the energy of the n-type region in relation to the p-type region by EV as shown in the figure. And the energy barrier needed for the electrons and holes to move to the p-type from the n-type, respectively, becomes smaller. At some applied potential, the conduction and valence bands of both regions align and charges freely flow from one region to the other. Thus, at some given potential, current increases significantly. How are all these measured? In practice, the p-n junction as a device complete with packaging and wires is called a diode. In the ideal case, the forward bias of the diode is represented by the red line. Below zero voltage, there is no current at all since a potential barrier blocks the passage of current. At zero voltage and above, the potential barrier is removed and current flows freely and is infinite. In the Shockley model, represented by the blue curve, current only begins at some specific voltage. In silicon, this is at 0.7 electron volts, and in germanium, this is at 0.3 electron volts. As we've seen in the previous slide, current begins to flow even when there's a small amount of applied voltage, and this is what we see in this figure. When the applied voltage reaches a certain value, the current flows freely. The current is not infinite, however, and increases with voltage, albeit quite fast. If we model the diode with an internal resistance R, then the behavior of the current with respect to voltage is depicted by the green curve. The slope of the curve is slightly tilted, and the tilting is an effect of the internal resistance of the diode. In this slide, you can see the current voltage characteristics of the various semiconductors. You can see, for example, that the current begins at 0.3 electron volts for germanium, while it begins at 0.7 electron volts for silicon. The slope of the curves also decreases because of the increasing internal resistances of the materials forming the diode. What happens in the reverse case when the terminals are reversed? If the negative terminal is placed on the p-type end and the positive terminal is placed on the n-type end, then the electrons in the n-type are attracted towards the positive terminal, while the holes in the p-type are attracted towards the negative terminal. This attraction causes the width of the depletion region to increase, which therefore increases the potential barrier. In the energy band diagram representation, this is represented by the lowering of the n-type region with respect to the p-type region. This symbolizes the difference in potential between these two regions and shows the further increase of the energy required to bring electrons from the n-type to the p-type and holes from the p-type to the n-type. Taking a look at the current voltage curves, In the reverse bias case, no current is allowed, so that there's just a flat line along the negative voltage axis. In reality, there's a small drift current and the voltage where the diode breaks down. When this happens, current freely flows in the negative bias region. Some diodes are specifically designed to take advantage of this feature. One such diode is called a Zener diode. The actual diode looks like the bottom figure. It is all black with a silver lining at one end to indicate where the side of the p-type material is or where the cathode is. In electrical symbols, the diode is represented by a triangle with a line at the pointed end of the triangle. The line indicates the cathode side. Some other types of diode are shown with their electrical symbols. These are the Zener diode, Schottky diode, the tunnel diode, the light-emitting diode or the LED, the photodiode, and the varactor. We'll discuss these types of diodes and their application in our next video.